значит, ну, там возможно, значит, там возможно, лаптоп использует неправильный микрофон, но что с этим делать, я не знаю. Okay, well, let's recall what happened last time. At the end of last week's meeting, I gave two definitions of a co-vibration sequence. This was the first definition, and the second definition was basically any triangle like shown, which after applying Hom to any spectrum W induces a long exact sequence of abelian groups. Yes.
The first definition of the right should be sigma x.
Oh, sorry. Yes, you're right. Thank you. Should be sigma A, or which is the same as A shifted by 1 to the left or to the right. Does anyone remember? No. Let's recall that sigma A ith component is sigma AI, which is which maps to the I plus 1 by the structure maps of the spectrum. So I plus 1 is the same as A 1 the ith component. So, we saw that this map is a weak equivalence, meaning it introduces an isomorphism of the stable homotopy groups. Very well, but So if I define AI, A of 1 as the spectrum whose ith component is AI plus 1, and the whole thing gets shifted to the left. For example, sigma, A1 of 0 is A, the first component. So we had A minus 1, A naught, A1, A2, etc. So the 0th component of A1 is A1. So this is A, this is A. Okay, does this picture make sense?
Yes, this is what I remember. A1 is shifted from A to the right.
No. It's shifted to.
A shifted to the left.
No. We get this one from this one by shifting it one step to the left. Well, it's sort of. I agree. It's sort of confusing. So let's. Let's sort it out before it causes more confusion. Okay, so anyway, and my claim was that these two definitions were equivalent. And we proved that 1 implies 2. Then we started proving 2 implies 1, but there was an assumption we made in the middle of the proof, and I said, let's think if we can get rid of it. And the other implication simply is not true as stated. Why? Well, we could take a triangle like this and then twist one of the maps by an isomorphism of either its source or the target. And then, for stupid reasons, the resulting triangle will not be isomorphic to the one we started with. But yet, the cohomology, the long exact sequence of the Homs will still be exact. So, for the moment, I don't know how to how to fix the second definition so that it works for all. I don't know how to restate this property in terms of long exact cohomology sequences, except by invoking the triangulated structure, which I don't want to do. So let's remember that we proved this, and the second implication is not true in general, and I invite everyone to think about how one can change the second definition so that it becomes equivalent to the first one, and it only involves long exact sequences and perhaps something on top of that, but preferably not too much. Are there any questions?
So if the two definitions are non-equivalent, what do we call collaboration sequence?
The first one. So we use the first definition, but we allow any isomorphic triangle, any triangle isomorphic to this one. We allow those as well. Okay, so once again, the reason the second definition is not equivalent to the first one, the way to state it is that we can take something of this form and mess it up using an automorphism of one of the objects. Okay, now. Another property of collaboration sequences is as follows. For every spectrum W, the applied to so we want to prove that cofibration sequences not only have exactness for maps from them, which is relatively straightforward, they also, and which also works for spaces. We want to do the same for maps into cofibration sequences, which is where we really need the suspension functor to be an isomorphism. Okay. Does this statement make any sense? So we take a sequence like this, and we apply W. We apply maps into W, and we want to show that the result is exact. No, it doesn't work. Okay, so well, if I have a map from W into A, then after composing with A to X to X by A, I get a null homotopic map. So one inclusion, namely the images in the kernel, is straightforward. Let's prove the other one. So suppose I have, let me call this I, and let me call this B. Suppose I have suppose I have a map, more precisely a partial map. I want to allow partial maps to get sufficiently many maps between spectra, so that there are enough maps to get everything in the homotopic category. Okay, such that F composed with P is null homotopic. And I want to lift F into A. In other words, I want to show that in fact F comes from A. Well, the first observation, since F is F composed with P is null homotopic, or we can extend we can extend the triangle to the square, which involves the cone over W. Does this make sense? And then basically, once I have a commutative diagram of two inclusions of CW complexes, I get once I have a commutative diagram of inclusions of two CW spectra, I get a map of the whole cofibration sequences, because well, firstly, this is the same as the previous space with the cone of the previous spectrum with the cone over X attached and so on. So we okay, so on the other hand, if I take the inclusion of W into the cone over W, I basically get the same result as for spaces. The cone over W mod W is the suspension of W, and what's the next term? What would the next term be for spaces? Well, basically, the cone is the trivial spectrum. Well, at least a homotype equivalent to the trivial spectrum. If every third element is trivial, then this means that the remaining ones are isomorphic. Okay, so we have these two arrows, and moreover, the third arrow, the last arrow, the one on the right, is sigma f just by the functoriality of the cofibration sequence. Oh, sorry. There's yes. So firstly, this is sigma W, and secondly, H I. G is something I'm looking for. I haven't quite found it yet. And And then basically use the fact that the suspension is an autoequivalence of the homotopy category. So this map I, which I have here, is sigma of G for some G from W to A. Does this make sense, Андрей? Имеет ли смысл хотя бы что-нибудь из происходящего? There are two. Oh yes. Yes. You're absolutely right. I'm running out of letters. Sorry. Let's change the psi into G into J. Thank you. So yes. So well, this is the inclusion. We don't really need it, but anyway. So we get the map G from W to A by taking J and desuspending. So I erase the question mark. And put G to be sigma minus 1 over J. And well, since this triangle commutes and sigma is an equivalence, this triangle commutes as well. Sorry, not triangle, square. So the one triangle commutes, hence so does the sigma to the minus 1 of the triangle, sorry, the square. One square commutes, so the desuspension also commutes in the homotopy category. Are there any questions? Well, so this statement is more useful than the first one, which is not surprising. So let's see a few applications of this. Firstly, we okay, let me X, Y. Firstly, we want to define the sum of two spectra. There are two ways. Later on we'll talk about products, but let's start with sums. And there are two ways to proceed. The first candidate is just take the component-wise wedge with component-wise structure maps. Here I'm using the suspension definition of a spectrum. And secondly, I can do the same thing with the product. This time it's more convenient to use the loop space definition of a spectrum to get the structure maps. The question is which one do we use? And does anyone know the answer? The answer is it doesn't matter. The natural map from the first to the second is an isomorphism in the homotopy category of spectra. Well, let me just put it like this. Well, why? To prove this, we firstly need to Well, we firstly need to reinterpret the homotopy groups in terms of maps from the suspension spectrum of some sphere. So I want to basically I want to apply this proposition, and I want to take W equal the suspension spectrum of some sphere. Which sphere? Yes. Well, this I is sort of a hint. Well, of course, this brings us to the question of what do we do if, for example, I is negative. There is no such thing as as the minus one dimensional sphere. Okay, well then I declare the minus one dimensional sphere to be simply so this is the sphere spectrum shifted by I to the left, and then using the fact that suspension is an isomorphism, I can shift it both ways, to the left or to the right, and then I will still have this equality. Okay, does this equality is this equality clear, or does it need any comments or explanations? Well, in general, it's complicated.
Yes, because it's linked category, and what do we do?
There is no universal recipe for computing the homes in the stable homotopy category. But this doesn't mean that we know in general how to compute either left-hand side or the right-hand side. We're just claiming that they're isomorphic. And so the spectrum here is basically what it says. It's a shifted sphere spectrum. So we take the normal sphere spectrum S0, S1, and so on, and shifted to the left or to the right, depending on the segment. Very well. Then we suppose we have an element here, and then we try to remember the definition. Well, it comes from a map of some sphere to some x, and then taking the image of this map in the direct limit. And then again, unwinding the definition, this gives us an element here basically representing the same element, and vice versa.
So maybe this is simultaneous. So partial maps of spectra are enough to represent homomorphic ones.
Yes, this is exactly why we want to consider partial maps. CW spectra are cofibrant, but not necessarily fibrant. So strict maps of CW spectra do not suffice in general, but I think we sort of proved, and maybe even without the adjective sort of, that if we take the homotypic category of spectra, localize with respect to pi isomorphisms, or with respect to, or we take the CW spectrum and localize with respect to inclusions of cofinal subspectra and component-wise homotypic equivalences, we get the same result, which is the stable homotypic category. And in any case, it's pretty straightforward that the inclusion of a cofinal subspectrum induces an isomorphism of the homotypic groups. So we don't, if we allow partial maps, we don't mess things up in the homotypic category. Because we invert maps which we need to invert anyway, namely the inclusions of cofinal subspectra. То есть новых каких-то, точнее новых схлопываний, значит, того, что не нужно схлопывать, не происходит, если мы обращаем включение полных, точнее, кофинальных подспектров, что мы делаем при определении вот этих вот частичных отображений. Мы фактически обращаем вложение кофинальных подспектров, но мы их и так должны обратить, и если мы хотим обратить, значит, всех, кто индуцирует изоморфизм в многомотопических группах. Ну вот, значит, то есть мы при этом не схлопываем те вещи, которые мы не должны схлопывать. Okay, so do I need to say anything more regarding this equality? Basically, my claim is we only need to unwind the definitions and the equality follows. Okay, now Now we basically use the fact that that the sequence is exact. And here we use this property of K-fibration sequences. And it's also it's also split exact because well, this map is induced by the inclusion of x in x wedge y, but there is the map in the opposite direction. So the map in the opposite direction. So the hom from W to X is a direct summand. So is hom from W to Y, and by exactness, this is all there is here. Normally, if we do not consider, for example, stable homotopy groups, if we consider unstable homotopy groups, the same works. This is a direct summand, this is a direct summand, but the sequence is not exact. So there is more here than what comes from X or Y alone. Does this make sense? Well, we could add zeros at the edges. We could add zeros on the left and on the right, and the sequence will still be exact. So for example, how to prove that this map is injective? Well, this map is injective because it has I don't remember, is it a left inverse or right inverse, but there is an inverse. So I can add a 0 here on the left. Similarly, why is this map surjective? Well, because it has an inverse on the other side. Does this make sense? Что у нас происходит? Значит, у вот этого отображения есть обратное, но только, естественно, с одной стороны, значит, оно индуцировано схлопыванием y в точку. Ну, замечательно. Значит, по тем же самым причинам. У вот этого отображения тоже есть обратное. Значит, оно индуцировано вложением y в букет. Здесь мы схлопываем x, а здесь мы вкладываем y в букет. Поэтому я здесь, значит, вот это отображение сюррективно, я могу написать 0 здесь. То есть нули я могу написать здесь и здесь, но это совершенно за бесплатно. What's important here is that we have a split exact sequence which after setting W to be a shifted sphere spectrum, we see that the homotypic groups of x wedge y are the same as the homotypic groups of x plus the homotypic groups of y, which is not at all true for spaces. And more or less by construction, the homotypic groups of this thing are the are also the product of the homotypic groups, and the isomorphisms are compatible with the map induced by the inclusion. So we get an isomorphism on the level of the homotypic groups, and the two spectra are equivalent. Very well. So this was one application. Another application. Suppose I have a CW complex, and Y spectrum. Then I can form another spectrum which I denote Y smash X, and which is obtained just by taking the components of y and smashing them component-wise by x. Very well. So my claim is x so the second application the homotypic groups of this smashed spectrum is the reduced homology theory for CW complexes. Now, does the before we prove this, does the expression a reduced homology theory make any sense? So we do what? So we need to check some axioms. Let's say we have a CW pair. Then my first observation by smashing the co-fibration sequence, or at least the beginning of the co-fibration sequence for this pair by Y, I get a co-fibration sequence for spectra. Well, then I use the same observation we used a couple of minutes ago. I interpret the homotypic groups as the Hom from a shifted sphere spectrum. So I take some shifted sphere spectrum, and I get I get some shifted sphere spectrum. I map it into this part of the Kerr-vibration sequence, and the result is exact. Why? This is the wrong way exactness for the Kerr-vibration sequence. So the sequence of the individual is it okay? So the sequence of the individual by i's is exact. Okay, so what else do we need to prove? We also need to prove the suspension isomorphism. And how do we prove this? Well, we simply use the exact couple, the CW couple CXX. Well, if we have something which is contractible, smashing every space against something contractible is contractible. So the same applies to spectra. If, for example, A is contractible, then Y smash A is also contractible, meaning trivial for every spectrum y. So the suspension isomorphism comes from the long exact sequence of the homotypic groups. And where does the long exact sequence of the homotypic groups come from? Let's see.
Мне кажется, можно воспользоваться ассоциативностью Нэша и перекинуть надстройку с x на y.
Да, наверное, действительно, да, совершенно верно, спасибо. So, what's your name?
Михаил.
What Mikhail is suggesting, we don't need to write the long exact sequence of the homotypic groups which corresponds to a cofibration. We simply need to remark that sigma x is the same as S1 wedge x. So we basically identify the spectrum y smash sigma x with y smash x, but shifted by 1. And so the suspension isomorphism simply becomes the isomorphism which comes from the fact that the suspension is the same as a shift, but to the left. And looping is the same as the shift to the right. Or we could use the exact couple, sorry, the CW couple CX, X and the long exact sequence. Now there's one other axiom we need to check. call this alpha. There's too many i's. Alpha, alpha. So suppose we have a family of based spaces, then we need to prove this this identity, which or isomorphism, which is the wedge axiom of a generalized homology theory. For cohomology theory, we would have a direct product instead of the direct sum, but here we have a homology theory. Well, what do we do? Well, if A, the indexing set is finite, then basically we can use what we already saw, namely the first application. If I have y wedge x1 so y smash x1 wedge x2. Okay, so by the way, why do we have this this formula? And is it true for spaces? So here y is a spectrum, x1, x2 are spaces. Is this formula true for spaces? Andrei, what do you think? Верна ли вот эта формула для пространства? Хотя бы с точностью до гомотопии, а может быть даже с точностью до, может быть даже там, если тут CW комплексы, они может быть даже вообще гомеоморфные. Давайте подумаем. So, is this formula true for spaces? Compactly generated Hausdorff. well, basically my claim is that for spaces we have a for compactor generated house of we have even a homeomorphism, and so the case of A containing just a finite number of elements is what we've done already. And if A is if A is infinite, then the spectrum we have on the left is the union of the union of the same type of subspectra, but we only include finitely many summons in the wedge. And if we have a CW spectrum, so let's say that Z has CW spectrum. Which is the union of subspectra, then the homotypic groups are the same as the direct limit or the co-limit of the homotypic groups of the subspectra. Well, again, this is okay. Those are CW subspectra. Again, so we have a natural map from the direct limit to this thing, and this map is injective and surjective. Basically, by remembering that an element here is always represented by a map of by a map from some sphere to some component of Z, and this map is by compactness of the sphere is in some is in the same component of some Z gamma, for some gamma. This shows that the map is surjective, and well, it's injective for a similar reason. Suppose we have an element here which goes to 0. Well, very well. Then this map is homotopic to the identity, but maybe in some larger subcomplex. And so it's already 0 in the direct limit. And well, combining these two observations, we see that the homotopic groups are the same as the homotopic groups of are the same as the limit, the direct limit of the homotopic groups of these spectra, and for these for finitely many summands, we already have the formula, so we get what we're after. Okay, I've run over time. Are there any questions? Okay, so the category of spectra has well, at least two monoidal structures, and we've seen the easy one, the sum, and there is a more complicated one, which is the product, and we'll talk about it after the break.